Hello everyone. I'm Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. I will be conducting the weekly tutorial sessions, and we will be discussing a few questions and problems based on the topics of the week. For week 0, we will be discussing questions based on the precursor to the course, the aircraft performance, and the contents of the first week. We'll begin with a simple question. It says the aerodynamic forces acting on an aircraft depend on what? The relative ground speed, wind speed, relative air speed, or none of them. So we know that when the aerodynamic forces are generated on an aircraft, when the aircraft moves in a medium, in air in this case. So all the aerodynamic forces, lift, drag, and all the others are generated by this motion of the aircraft through the air. So the equation that we use, the half rho v square, the v in that is the relative airspeed. That is the relative airspeed between the aircraft and the oncoming velocity. The angle of attack and all the aerodynamic parameters are analyzed based on this relative airspeed. So the answer to this question would be relative airspeed. This is from the aircraft performance course. Next question deals with the aerodynamic center. So which is correct about the aerodynamic center of an aircraft? Aerodynamic center does not depend on location of center of gravity. It depends on location of center of gravity. It depends on neutral point or none of these. So as we have seen from the first week, the aerodynamic center is the point on the cross section of an airfoil about which the pitching moment coefficient is constant. So constant with angle of attack. So that is how the aerodynamic center of an aircraft is decided. It does not depend on the location of center of gravity or the neutral point or any other characteristic. It depends only, it is defined as the point about which the pitching moment does not change with angle of attack. And just to note here, neutral point is like the aerodynamic center, but for the entire aircraft. So that is how the analysis is done for the entire aircraft, and aerodynamic center for an airfoil. So the correct answer to this would be the first one. Aerodynamic center does not depend on the location of center of gravity. Continuing from that discussion about pitching moment coefficient, if the cross section of the wing, that is the airfoil, is symmetrical, what will be the pitching moment coefficient at 0 degree angle of attack? Now, how is this pitching moment created for a wing? The forces, lift, all the aerodynamic forces are said to act about a point called center of pressure. Now, the center of pressure for an airfoil changes with angle of attack. So if your airfoil, bear with my drawing skills, if this is the center of pressure and this is your aerodynamic center, the forces acting here produce a moment above the aerodynamic center. And this is the pitching moment. And this center of pressure moves ahead with increase in angle of attack and moves behind, moves towards the trailing edge of the airfoil with decrease in angle of attack. So it becomes very inconvenient to analyze the forces acting at center of pressure because it changes throughout the entire flight duration. So we have come up with a point called aerodynamic center as we defined in the previous question. It's the point about which the pitching moment remains constant. So when we transfer the forces that act actually at the center of pressure to the aerodynamic center, it comes with a moment. So the forces acting at the center of pressure when transferred to the aerodynamic center comes with a moment as discussed in the first week of this course. Now, if it's a symmetrical airfoil, it so happens that the center of pressure and aerodynamic center are same and they do not change with angle of attack. So I believe this is one of the questions of your assignment. So I'm not going to give the answer directly, but from this discussion, I think you should be able to answer this. So for the symmetrical airfoil, the center of pressure and aerodynamic center are the same. We have discussed that lift and all the other aerodynamic forces act at the center of pressure. And I've told from the previous question that the pitching moment at aerodynamic center does not change with angle of attack. These 3 points I think would suffice for you to answer this question. So let's move to the next one. So we discussed for a symmetrical airfoil, for a positively cambered airfoil. That is the diagram that I drew a couple of slides back. Yeah, so this one. It doesn't look cambered, but for a positively cambered airfoil, considering that leading edge up, that is nose up, is positive moment, what would be the pitching moment about the aerodynamic center? For a positively cambered airfoil, where do you think the center of pressure lies, before or after the center of aerodynamic center? Now, the aerodynamic center for typical airspeeds, low airspeeds for typical airfoils is at the quarter chord point, and center of pressure for positively cambered airfoil lies after the aerodynamic center. And as discussed previously, lift acts at the center of pressure. And again, just to note, for a positively cambered airfoil, we know the CL versus alpha. It produces a lift even at zero angle of attack. So with these points, I think you should be able to answer this, as this is again one of the questions from the assignment. I will not be telling you the answer, but I think these 2 points should suffice. Moving ahead, we discuss aspect ratios now. Aspect ratio is the ratio of the square of the span to the surface area. Now, what happens to the aspect ratio when the aspect ratio increases or decreases? What happens to the lift curve slope? Lift curve slope is the slope between the CL, slope of the curve between CL and alpha. So, what is the difference between a 2D wing and a 3D wing? 2D wing is infinite wingspan. So the B, so aspect ratio here is B square by S. The B in this case would be infinite for a 2D airfoil. And for a 3D wing, 3D that is a finite wing, you have the difference between those two is that you have tips. Now what happens because of this tips is that the flow from below the wings try to come above the wings, and you have wingtip vortices generated. And when you have wingtip vortices generated, there tends to be a downward component of velocity that acts on the upper surface of the wing. This is called downwash. Again, something that's discussed in both aircraft performance and the first week of this course. So what happens aspect ratio, when it decreases, that is the wingspan decreases. When the wingspan decreases, a larger portion of the wing is exposed to these wingtip vortices and downwash, and then the lift decreases. So for the same angle of attack with a lesser aspect ratio, the lift produced would be less. So what does that mean? So if we draw the CL versus alpha diagram again, considering this is for aspect ratio infinite. Aspect ratio infinite is when B is infinite, that is the wingspan is infinite. That is for a 2D airfoil. If this is the lift curve slope for aspect ratio infinity, with decrease in aspect ratio, that is when it becomes a 3D wing, this is how the change occurs. So what we see is with a decrease in aspect ratio, suppose 10 or 5, there is a decrease in the slope of the lift curve slope. So that would be the answer to this question. Continuing the discussion on aspect ratio, what do winglets do to aspect ratio? So what are winglets? Winglets are those curves at the tips of the wing that are introduced to reduce the effects of downwash, reduce the wingtip vortices. So what do they do? So the winglets contribute to an increase in span. So aspect ratio was B square by S. They contribute to an increase in the wingspan B, also contribute to an increase in surface area. But since this is a square component B, it effectively increases the aspect ratio. Best part about it is that the actual wingspan doesn't increase, just the component used in the aspect ratio increases. So the answer to this question would be, it increases the effective aspect ratio. Winglets increase the effective aspect ratio. Now, continuing the discussion on stability. So for a static stability level, slope of CM versus CL alpha, a CL is given to us, and the pitching moment at zero lift is also given to us. They've asked us to find the trim lift coefficient. So the equation used to solve this question is this. Now, how did this equation come about? In the first week of this course, you would have seen the equation for pitching moment coefficient, which is Cm equals Cm naught plus Cm alpha into alpha. Now the Cm alpha we can manipulate to get terms that involve Cl, because those are the values given to us in this question. So that would be Cm naught plus the slope dCm by dCl by Cl alpha, and this alpha remains. Now this value is given to us, and Cl alpha into alpha is nothing but Cl. So that is the equation that I've written below in blue, Cm naught plus dCm by dCl and Cl. dCm by dCl, the value is given to us as minus 0.02. And Cm naught is given to us. That's a pitching moment coefficient at zero lift. Now it says what the trim lift coefficient will be. Trim is the condition of the aircraft when all of the moments and summation of all the forces and moments are zero. So in this case, our Cm would be zero. So it becomes Cm naught equals minus dCm by dCl into Cl. And Cm naught is 0.055. And this becomes 0.12 into Cl. Now this Cl you can find out by just doing simple calculations. So this is a simple equation used for the stability, longitudinal stability of an aircraft. Now, this is from the aircraft performance course. What is the primary control for yawing motion? So I hope you know the control surfaces of an aircraft. I've just put a picture just in case. So the three control surfaces are, these are the ailerons. Ailerons are on the wings. They are used to control the rolling motion. We have elevators used to control the pitching motion. Pitching motion is about this axis as shown here. And a pitch up, that is nose up, is considered positive. A rolling direction towards the right is considered positive. And the question here is yawing motion. Yawing motion is controlled by this control surface, which is the rudder. And the fourth option here is throttle. Throttle is used to increase the magnitude of velocity. You know what a throttle does. This is a very simple question from aircraft performance. The last question is, stalls normally occur on what part of the wing? We hope that the stall occurs on the wing root first, and that is what happens in reality. Why does it happen? So what is a stall? Stall is when at a particular angle of attack, the boundary layer detaches from the wing or the airfoil such that there is no aerodynamic force generated in that region. So that is when the stall occurs. So at wing tips, due to the before mentioned wingtip vortices, there is an effective reduce in the angle of attack. The angle of attack that the wingtip sees is lesser than the angle of attack that the wing root sees. And this is due to the wingtip vortices. One of the benefits of wingtip vortices that you can still control the aircraft even if the wing root stalls. So what happens is the boundary layer detaches from the wing root first, and then due to this effective reduction in angle of attack at the wingtips, the boundary layer is still attached to the wingtips and the stall doesn't occur. So you can control the aircraft once it has stalled at the root. So the answer to this question is wing root. Wing root is what stalls first. So with this, we complete our discussion of the first few questions on week 1. So I hope these discussions help you in solving the assignment. Some of the questions are directly from the assignment, so you should be able to do a good job. So we'll see you next week.